Review of one of the topics we talked about at the first of the year. So who came up with the law of conservation of matter?
Aristotle.
Close. No. No. The father of chemistry? Lavoisier. Now, Lavoisier, father of chemistry, came up with the law of conservation of matter. So we're going to do that lab tomorrow, right? So last week we introduced alpha decay. We talked about Claire Patterson. What did he do? Raise your hand. Claire Patterson points. Raise your hand.
What was the question?
Last week we talked about alpha decay and Claire Patterson. What did he do?
Oh, he determined that everything is an electron.
Raise your hand.
Gamma rays.
No. I said alpha decay. He determined alpha decay. So what specifically did he use alpha decay to do?
Never heard that one.
It's posted on your Google Classroom. It had to do with the age of the Earth. Claire Patterson was responsible for the age of the Earth. Yes, uranium. Yes. He used uranium. Shh. Kristen. He used uranium to age the Earth. So you might want to write that down in your notes. That uranium was used to age the Earth. And what did he look for in meteorites that came to the Earth?
Uranium.
No, he looked for lead. Because lead and iron do not mix. So he found the isotope percent composition in the lead was different than that of the Earth. There were different amounts. So he noticed that uranium decays into lead, so he figured out that the decay of uranium to lead could be a way to date the Earth. So that's what he did. Uranium decays into lead. Write that down. Uranium decays into lead. He looked at meteorites. Meteorites do not contain any uranium, so they cannot produce lead. So he noticed that there's a different composition of the lead isotopes in the meteor compared to what's on the Earth. Does everybody see that? Okay, lead is very dangerous to you, yes. But he also helped in removing lead from like paint and gasoline, so that's why we have discussed him for a couple days, because he had a big impact on the health and the memory of Americans. Number 1 for the bell, or letter A for the bell work. Anybody?
Have we gone over this?
Shh. Yes, we introduced it on Thursday. I'm just seeing if you can use your brain and solve. Give it a try. Yes, we were off Friday. Coming week. Today is America Day. And Kai, I love your American spirit.
Thanks.
So we need a marker.
That's the smallest number I've ever seen. What, 213?
Helium. Right. It's helium, right?
Okay.
And that's 4.
Excellent. Nice job. Points. Okay, you're close, but that is not correct.
I'm just going to put down random letters and hope I get it right.
Oh, TH.
That's what I'm doing.
How do you know the first one is
Right, do you have to know the periodic table for this?
We'll explain it here in a minute.
That's a 0.
okay.
Nice job. Okay, nice job. Excellent. Where you see the 2 on the HE is the atomic number. So then you go to the periodic table and you will find the atomic number. The atomic number is a small number. So in the back of the book, there's a periodic table. And you'll see that number 2 is helium, right there. So it tells you the symbol is He. Now, there are a couple that you'll have to kind of know. That would be the beta particle. Is one negative and the symbol is E, or a B, and then it has 0 mass. So some of these you'll just have to reference. I might put them on the board up here just because we're new at this and I don't want to overwhelm you. So I'll put that up for you. I'll be nice because this is new. This isn't Chemistry 4. It's Chemistry 1 to you. So any question on that? Assignment associated with the writing expository. You can go to Google Classroom. It's right here. So you're going to click here and you'll see the assignment. Then you can scroll down and you will see examples of student work. So you can click on that as far as what we expect you to do. So you can click right here, and it'll take you to an example by Rachel Durbin. She did hers on Louis Lior.
Is that like from the studio?
Could be. Now, what I want to do now, I want to show you how to use Pixlr, how you can photo edit a picture like Rachel did. You can see right here how she put the Nobel Prize next to her picture. You want to have a picture in your article because that's going to put you in the direction of promoting yourself. People will remember you two ways. They'll remember you by your looks, and they'll remember you by your name. So the more they see you, the more chances are that they'll offer you more jobs. And more jobs always means more money. Bring here into our picture. So that's what we want you to do for your Nobel Prize expository paper. Now, what does expository mean? Max? Shh. What does expository mean?
Isn't that like pooping?
Now, if you go back to your
Or an expository something that goes in
online doc, it tells you what expository is. It says basically that it is researching. Expository writing is explanatory. You select information from oral, written, or electronic text and organize it to show that you understand the concept. So you're just basically trying to show that you understand what the Nobel Prize winner did, why they got the Nobel Prize, and how it impacted your life and my life. And then you're going to put a picture next to them. So it's really, it's really simple writing, but it's digital backpack. We're just trying to get an item in your digital backpack.
Gamma rays does not change the atomic number or mass number of a nucleus. Gamma rays almost always accompany alpha and beta radiation, as they account for most of the energy loss that occurs in the nucleus decays. For example, gamma rays accompany the alpha decay reaction of uranium-238.
Okay, very good. So up here we have a Geiger counter. So does anybody know what a Geiger counter is?
No.
Yes, it measures radiation. So Geiger counters are very sensitive. And let me read about the gamma. And we have here some cobalt-60, which is radioactive. Now the Geiger counter basically has gas inside of this container, and as the ions go into the container, it ionizes the gas particles and it sets off a sensor. So as I turn this on, you can see that you don't really hear anything. Just when I turned it on, right? Does anybody hear anything?
Oh, I know.
I'm just like, I don't hear much
Clicking
shit
it.
because
That's all I hear. All I hear is you clicking your finger.
I've watched
Okay.
a video of people walking through Chernobyl, and they have those things, so they go, you know?
Now you probably shouldn't handle this because it is dangerous.
that's radiation.
Yeah, it's giving off radiation now.
You could die right
Why is it here?
Oh, we can't.
What if I get cancer?
Well, I mean, I wouldn't want to walk around and like hold that all day. Did you hear, the gamma coming off of that? Now let's look at the beta. This is SR90. What's SR? Raise your hand. Points. What's SR? What? What's the symbol? Well, obviously the symbol is SR. What's the name for SR? You're close. Strontium. Yes, it's right below calcium. You'll see right there, strontium. So we have some strontium. We just looked at cobalt, which is right next to iron. So let's take a look at the strontium. That is a beta decay. Strontium 90.
Whoa!
So this is reading about
Can we
1.
see it?
Yeah, you can see here it's reading around 1 on the counter.
Ow.
Could I show
Whoa,
you?
man. Keep that and hurry up.
Well,
How I've changed.
that's 1.
Shh.
The gamma is
What is that?
gamma's going to about a 3.
Wait, is that bad?
It's just more radioactive. Yeah, the gamma's more dangerous.
Wait, is that like going to those ghost meters?
Well, you shouldn't handle it probably like I'm handling it, but I'm not doing it.
Wait, what if you swallowed one of those?
Well, it wouldn't be good for you.
Look, see, that's
Yeah, it would be very bad for you.
Okay, but how long would it take for me to die?
Probably a day or two. I'll get some tongs next period. All right, the last one is the alpha particle. All right, and you can see here.
So that has 0 meaning?
It is. Yeah, listen.
Wait, so what's it?
It's the alpha. Most likely, it's not the alpha that's causing the sensor to beep. It's the other particles that are coming off with the alpha. It's just not as radioactive. What's that? Like in Laurel. Laurel, if you come up and do letter A, I'll give you 3 points. It's pretty difficult. Anybody else? How about, all right, Aiden. I did on the first 6 weeks the bell work, so you should have noticed that you got 10 points on that. Okay. Go ahead. Freddie. There's a black marker there. Let's give it. Okay, good try. And how about the next one? All right, let's go with 8. Okay, 8, you get to pick who goes next.
Buddy?
Your attention to, hopefully, raise your hand now if you have no idea how to do this. Raise your hand if you have no idea how to do this. Okay, so on the sheet that I gave you when you walked in, all we've done is the 3 examples. 1, 2, and 3 are on the board. So the answers are there. All I did was put in boxes where the information is missing. So if you look on your paper, you'll see that this is the exact same thing for the bell work. The first one, there's a box where you see 42HE. So over here you see 42HE. So the people that answered this are observant. I did not tell them the answers were there. They just kind of looked. That's life. I mean, if you're observant, you tend to do well in life. Those people that are observant tend to be the advanced people. And then, you know, the workers tend to be another sector. So that's what advanced people struggle with the most, is working. That is doing the same thing over and over again. So up here, you see that 90 plus 2 is what? Yeah, 92. So this is very important, these lower numbers. They call these the atomic numbers. And the 2 tells you what? Tells you the symbol. So then if you didn't know what the symbol is, you have to go to the back of the book and look at the periodic table, and you find the atomic number, and the atomic number for 2 is the symbol He. So as we progress with these, if you're trying to fill in the blocks, that's how we do this. The bottom number is the most important. The top number is going to tell you the what? What does this tell you? Starts with the M. Tells you the mass. And for every isotope, the mass is different. So you can't go to the periodic table and find the symbol because the isotopes are different and they have different masses that could point you to a different element. Is everybody clear? So you have to use the atomic number. The periodic table is organized based on the atomic number. Any question on that? What example did we give for alpha decay? Anybody remember? Yes, it was uranium, Hunter has a good memory. Specifically, why is uranium important? Why was that example important? Yeah, it talked about the age of the Earth. So if you don't have that in your notes, you should probably write that there. The uranium was used to, in science, date the Earth. And what did he look for in meteors? He looked for lead. He found the lead isotopes in meteors. And they had a certain percent composition. There was lead 204, 206, and 207 found in the meteors, which was in a different percent composition that was found on the Earth. So he figured out, okay, so if uranium is making 206 and 207, it's going to account for that extra lead, and then you can give a half-life, determine how old the Earth is. That's what he did. So he used uranium to date the Earth, which is pretty cool. I mean, when you're thinking about it, an experiment, and you're trying to prove something to somebody with data, that's a really, really good experiment. All right, so today we're reading on in the book about beta and gamma. Who's going to read for us? Laurel. We're on page 860. Ionizing. All right, let's say we have a substance like Fe2+. We have a alpha particle, it's a cation, right? If I bring in electrons, right, I am doing what to that? Am I reducing it, or am I oxidizing it? I'm reducing it. I'm giving it electrons to reduce the charge. It has a 2 positive charge. So if I have a substance in here that I can, let's say, give electrons to, because this strontium is releasing electrons. Does everybody understand that? The beta particle is an electron. Write that down if you didn't know it. The beta particle is an electron. And ions basically are charged particles. The cation is a positively charged particle. The anion is the negative one. Now the anion is the one we typically associate with the electrons because it has extra electrons. It's negative. Like chlorine in the water would be an anion. It has electrons. So as I give this electrons, it's ionizing. What's ionizing in here? Anybody know what's ionizing in here? In the Geiger counter, what's ionizing would be this gas. So you can see right here it says there's a gas atom, right? And this energy strikes the gas atom, causing it to ionize and hit this sensor. So the electrons are causing the gas to ionize. So when I take it away, it's no longer ionized. Now, how do the gamma particles cause ionizing? Ever heard of a solar calculator? A solar calculator uses light to ionize the solar panel to get the electrons to move. So you can really do the same thing with the gamma particles that you're doing with the beta. Works both ways. The gamma, if it's releasing a lot, I think the one we have here is relatively stable compared to some other isotopes, because you're just talking about the danger level. They couldn't give us a super dangerous gamma producing particle, right? It had to be equivalent to the beta. Actually, it's probably less damaging than the beta, because gamma is so dangerous. I mean, it affects your DNA. Everybody clear on that? The beta is not going to affect my DNA as much as the gamma is. All right, the last one we're going to look at is the alpha. And this one is PO. What's PO?
Polonium.
Polonium. Very good, Hunter. Polonium. Now, if I put this up here, why don't you hear a lot of ionization happening? Yeah, it's not going to be ionizing the gas very easily. You did hear one click. Very good, Nathan. Excellent. Can anybody do letter B?
radiation. If it's gamma radiation, how's it going to cause it to ionize? Anybody ever seen a solar calculator?
Yes.
So solar calculators can't influence electrons. So once it becomes negatively charged, it's going to be attracted to the anode part of the sensor. Letter A, 3 points. Yeah. That is correct. Nice job. Anybody else do letter B? All right, let's go with the girl. Let's go with Summer. Lowercase e. First letter's capital, second out has the answers for the bell work on it, on the board. Now, the reason why I did this, the reason why I put the answers on the handout for the bell work is we're introducing this topic. So I don't want to give you something you can't look on as a reference, but I do want to draw your attention to the 2 underneath the HE. That 2 corresponds to what? What does that 2 mean? It's the atomic number. So it tells you the symbol in the periodic table. So you go to the periodic table, you find the atomic number 2, and it'll say HE.